So let's take a small example. Okay, so let's take an example here. So I have got 1 and 1 0 0 1. Okay, so let's try to add this. If you're going to add this, I'm going to get 1 plus 1 is equals to 0 1, right? So that's my first ripple. 1 plus 1 0, again 0 and 1 over here. That's my second ripple, and it's going to get a 1 over here, and 1 plus 1 is 0 1 over here, right? So I have got two ripples, and okay, so this is not the worst case because they are just two ripples, and my answer is so. I'm just going to talk about first of all ripple carry adder. Now, um, yeah, Said Hail Adder Hail. Okay, thank you. Okay, so I'm just going to talk first about ripple carry adder, how this ripple carry adder works. Now, what happens is in the last class also I discussed about this, that when I'm going to give this input, so you can imagine that there are four full adders, right? So there are four full adders, and these full adders are getting two inputs to them, right? So they are getting these two inputs. Wait, I'll just draw it with a different marker here. Okay, so these are the two inputs that they are getting, right? So everyone is getting two inputs. So there are four full adders, but a full adder has got three inputs. So the third input is actually the carry in coming from a different stage. So yeah, this one here, this one goes over here, this one goes over here, and this one goes over here, right? So we have four full adders, but then there is one thing more over here, that we have a carry input. So this carry input goes over here, this one goes over here, this one goes over here, and this one goes over here, and then finally we have a carry out, right? So this is how we design a ripple carry adder. So there are four full adders, and then they are working like this. Now, and all these full adders are combinational circuits. So whenever they get the input, they are going to give an output, right? So what would be the output in this case? So there would be some output coming. So what would be the output in this case? So it's going to get 1 1 and some carry input over here. So this is going to give, let's say the carry input is 0. So it's going to give a 0 over here and a 1 over here, right? Okay, what will this give? So this one is coming from the previous full adder, and it's going to come after some time, right? But before that, what it had was just 1 and 0. So it's going to add just 1 and 0. And here the carry input would be 0 initially. So it's going to add just 1 and 0, and it's going to give a 0 over here. Oh, sorry, 1 over here. So it's going to give a 1 over here, right? Similarly, a 0 plus 0 and 0 coming from this side is going to give a 0 over here. And a 1 plus 1 is going to give a 1 0 over here. Okay. So this is our first step. Okay, this is our first step. Now what happens is there is a 1 coming from these two first bit. There's a 1 coming from this, and this 1 is added with 1 and 0, and so this full adder is going to give a different result this time. Now this result is confirmed because 0 is the first stage, but you are going to see, but because of this 1 over here, right, because of this 1 over here, the second full adder is going to change its output. So now it's going to add 1, 1 and 0. So this is no more 1 over here. It's going to be a 0 over here and a 1 goes over here. So, right? And because of this, okay, so this is again the second step, and the remaining thing goes the same. The other thing goes the same, 0, 0, 1. So this is going to be our second result, second step. Then the third step, what you're going to see is, because of this one, the third full adder is also going to change itself, because now it's going to be 1, 0, 0. It's not going to be 1 anymore. It's going to be a 0 anymore. It's going to be 1. So now this is going to change, right? And this is going to become 1. So this is going to be our third step. And since it's not going to generate any more carry out, so you're going to see that your final result comes after these changes. Okay, so it's not immediately that you're going to get this result, right? But it's something like it's progressive. So initially, immediately you're going to get this result. Then after some delay, because the ripple effect is going to go in, you're going to get this result. Then again it will produce some more ripples, and then you're going to get this result. So since this has not produced any more ripples, you're not going to change this result. Had this been a 1 over, had there been a 1 over here, you would have seen there would be one more ripple, and that's the maximum that can happen, because there can be maximum 4 ripples in 4 bits. So then you can see that there would have been another step where you're going to complete your result. So in a ripple carry adder, it takes time to get the right result. Okay. Now the problem in this thing is, the more bits you have, the more time it's going to take. Is this clear up till now? All three of you? Is this clear up till now?
Yes, sir, this is clear, Carrier. But just one thing. Uh,
Huh?
every time all the full adders would be compiling their
Yes,
answers.
yes, 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 yes. Because all of them are there. There are four full adders, and they are always going. And any combinational circuit, you cannot prevent it from giving any output. Okay, in a
Uh,
sequential circuit, what happens is you have registers, and
okay.
these registers are operated on a clock, right? So you can manage that input change if you manage the clock. So if you're going to have a particular clock coming in, it's only going to get the inputs at that point of time, and it's not going to change. But if you're going to talk about a combinational circuit, there are no clocks there. So whenever a new input comes, it's going to change itself. So if you're going to see the design, as we have mentioned in the last class, full adders are simple and or gates, right? So if you're going to give a 1 0 at the input of that gate, it's going to give an output, right? So what's happening is, it's these two numbers are already going to be provided to all of these four full adders. The only thing missing is the carry input. Okay, but that carry input is going to come at some point of time. So it might happen you get a result immediately in the first step, because there are no ripples, and that's your answer. That's the best case. But it might also happen that you have got maximum ripples. So in that case, it's going to keep on changing itself until your final answer is ready. And whenever we are going to design any circuit, we are going to always consider its worst case time. So that's the problem with ripple carry adder, that the worst case time of that adder is high, right? So if it's a 32-bit adder, it's going to give the result in 32 bits, 32 steps, right? The maximum delay that's going to happen. When we talked about carry skip adder, so we said that what we can do is break that into blocks, and each block is going to be then considered as either a propagating block, a generating block, or an absorbing block. Now, carry skip adder is not going to benefit very much in this small number, 4-bit. For carry skip adder to see its potential, you need very big number, so that you can see that the advantage is coming. Because in that case, if I'm going to break this into two blocks, each of 2 bits, then you're going to see that there is no big advantage of carry skip adder in this case. But if I had a bigger adder, and then if I break that into blocks, then you're going to see that if the carry input to that block is known ahead of time, then we can obviously go to that step immediately, right? So what happened in second step was because of this full adder which has produced the result after the second step. But if in the first step, if this full adder could have known what the input would be, this is going to happen in the first step, right? So that's what carry skip adder is going to do. Now we talk about the carry select adder. Now in a carry select adder, we said that we are not going to do it this way. Okay, so I'm going to take the same example, 1011 1001. So 1011, okay, 1011, and what was that? 1001, 1001. Okay, now let's try to do it in the carry select way. Now in a carry select way, I'm going to break that into again half of that. There are no blocks over here, but I'm going to initially start with half, right? So if it's a 32-bit number, I'm going to have 16 numbers. Okay. Now this thing here, 1010, is going to be given to a set of two full adders, right? Okay. That was normal in replicary adder, but here now what we are doing is instead of two full adders, we are going to have say four full adders. Okay. Now this is a little interesting over here, because why four full adders? Now these two are connected, but this input over here, one of them is going to get a 0, the other one is going to get a 1, because these are the only two options that can come from this side. Okay, either a 0 or a 1, right? So if it's a 0, then this answer is correct. If it's a 1, then this answer is correct. Okay, so we are going to pre-compute with both of them. So what, on the other hand, what we have are just two full adders as previously, right? Okay, so and they are connected in the same way. This is the carry input. So you see one goes over here and the other one goes over here. So one goes over here, the 0 goes over here. But in this case, the 0 and 0 are going to go to both of them. Similarly here, and this 1 and 1 is also going to go to both of them. Similarly here. So they are going to get some now you have determined their carry inputs. So this is as if this same thing is working like this. So it has got this carry input and it has also got this carry input. So all of them, these two and these two are going to work at the same time. And these two and these two are also going to work at the same time, because all of their inputs are now decided. So by the time you're going to get this result, you're also going to get this result and this result. Right? Is this clear? So you're going to take just 2 cycles, 2 steps to get any of these results. Right?
Yes, I got it.
Okay. Then what happens is if that output from after 2 step is 0, you just have to simply select this result and merge it with this result to get your answer. You're not going to do any computation anymore because you have pre-computed that result with a 0 input. So you said, okay, once you know that output is 0, you're going to just select this result, merge it with the other part, and this is your answer. If that had been a 1 over here, if there was a 1 over here, then what you're going to do is you're going to select this one and make that as your answer. That's it. So what's left is just a selection, right? And for selection, we have a multiplexer over here. Now look at this design and the previous one. So here we had four full adders for 4 bits, but here we have increased the number of full adders, right? Increase the number of connections as well, right? And also introduce a multiplexer at the end. So the hardware has increased, but the benefit you are getting is half of the time, half of the time. Now if okay, I'm going to come back over here to my presentation
Just,
and
at this moment, uh,
yeah,
just can you there's a CN which is coming from the to the first one adder, the first
yeah,
K by 2 adder. This
yeah.
is definitely zero all the time, right?
Uh, yes, if that result is not coming from any other input, it's zero.
If we are
But
doing a fresh addition.
okay, yes, it's zero then.
Okay, okay, fine.
At zero, then it's predetermined. That's the only thing predetermined over here. That only carry in. But in carry select adder, we have also determined their carry inputs. One of them is zero, another one is one. Okay, so this makes sense here because these are only two options. We cannot have any other option over here. We cannot have a 1 0 or 0 1 combination or any other number. So all these two inputs are given as all these possibilities are given as input, and you all these three are going to work at the same time because they are of same sizes. So it's going to take the equal time. So by the time you get the result over here, you also get the results on these two k by 2 bit address as well. So then if that result is zero, you're going to select the zeroth result to be your final answer, half k by 2 bits. And if that result is one, you're just simply going to select that answer. So both of them have been pre-computed, right? Is this okay?
Yes, so now it's clear.
Okay, so but this design does not stop over here. Before I go to the next design, I'll just share with you the cost and the timing figures over here. So as we have mentioned here, the cost in this case would be three adders of k by 2 plus k by 2 plus 1. That's the multiplexer cost because there are k by 2 plus 1 multiplexers over here, each of 2 to 1 multiplexer. So it's getting two inputs and is 2 bits and getting 1 bit output. So there are k by 2 plus 1 because we need one more multiplexer for the carry outs coming out of these two. So that has to be the same as well. So if one is selected, that carry out has to be selected. If zero is selected, its carry out has to be selected. So actually this is k by 2, but this is k by 2 plus 1. So your final answer is actually k by 2 plus 1, k plus 1, sorry. So your final answer is k by 2 plus k by 2 plus 1, right? So this is the cost over here. So you need k by 2 plus 1 for this multiplexer. The time over here, obviously, this all is done in parallel. So the only time is equivalent to a single k by 2 bit adder. So the time of a k by 2 bit adder is represented as t add k by 2. This one time is for this multiplexer. So it's going to take just one cycle and it's going to determine the result, right? So you can see that the time is halved. The time has been halved. So it's half from, so if k is 32, it's just going to take 16, maximum 16 ripples to give you the answer. 16 plus 1, 17 ripples to give you the answer. 17 units to give you the answer. Okay, so now let's move on to its. So what we can do is have even smaller ripples, ripple adders, so that many of the things can be done in parallel. So let's go to another design here. Now this is again a carry select adder, but this time we have a k by 4 bit adder. Now we have shortened the size of that adder so that there are fewer ripples. Now, if you are talking about 32-bit additions, so what you have done is you have 32 by 4 or 8-bit adders. So now you have an 8. So this design over here, as you can see, is actually what was there previously as well. What we have discussed in the last slide. So this is the same thing, except that instead of k by 2, it's k by 4. So this was there. Now when you have the other half, Now, since this was the first one, you know what Cin is. But when you go to the second half, you don't have an option at this point. So you are going to have both 0 and 1 in this case, right? And then its output is going to go to another one. So you need a 0, 1 at this case as well, right? So you, in total, what we have done, we need 7 k by 4 bit adders. So instead of just 4 to do this job, we need 7. Except for the first stage, we need 2 k by 4 bit adders at all these levels. Okay. So k is whatever number is there. If you're dividing by 4, you need at least 4 different k by 4 adders so that you get the final result. Now, and if you divide it into two halves, you're going to see that these three, and these four are going to work at the same time. So in total, you can say that all of them are going to work at the same time. But once the result of this zero is there, the result of these are also there. Okay, now it's quite simple. That's why I have, since I have discussed about the previous design, you can then say imagine it yourself or try to think it yourself that this was with C in a single, but here we have got 0 and 1. So if there are two inputs over here and two over here, so the possibilities over here are four, right? 0 0, 0 1, 1 0, and 1 1. Okay, so 0 is input coming from this side, and the result is 0. So that would be 0 0. 0 is coming from this side, but the result is, the carry out result is 1. So 0 1. So 0 can combine with 0, 0 can combine with 1. Similarly, 1 can combine with 0, 1 can combine with 1. So what we need over here are two different multiplexers, and then you can have 0 with 0 or 0 with 1 and 1 with 0 and 1 with 1, right? So instead of one multiplexer over here, because there was just a single number that's going to come over here, but here we have got two k by 4 bit adders, so they you need two different multiplexers at this level, right? So that's the only change over here. Both of them are getting the same input at the 0 input, and one input, their inputs are same, right? So if 0 is over here and 0 is at the output, you're going to select that output over here, which is going to go on this side of the multiplexer. So finally we need another multiplexer, right, to select between what is required, and then we are going to select what is there. So 0 with 0 and 0 with 1. So 0 with 0 and 0 with 1, and 1 with 0 and 1 with 1 is all going over here. So if it's 0 on this side, you know what 0 and which one was selected over here. So that input has to be selected, and this is going to finally be your answer. Now you can go through that yourself. It's not very difficult. Maybe there is not much of a time over here to go through it completely for you people over here. But if you're going to do that yourself, you're going to see it's not very complicated. So the point I want to mention over here is that we have shortened the ripple effects. So from 32 to 16, and from 16 to 8. Now 8 means that all 8 ripples over here, here, and here are going to happen at the same time. So this whole thing is going to take just 8 steps maximum, right? So nothing more. Plus there is one level of multiplexer over here, another level of multiplexer over here, right? So you have 8 plus 1 plus 1. So same 32-bit number can now be done in 10 steps, in 10 units of time, right? So they can be 10 maximum unit of times for 32-bit number. So now you can see that it's no more linear. It's no more dependent on k. It has gotten logarithmic. So these are log errors because what you're doing is you are having layers of multiplexers over here, levels of multiplex. Sorry, you're having levels of multiplexer over here, multiplexer at this level, another level, another level. So what you can do is you can go to another level. So instead of k by 4, you can go for k by 8 as well. Now if you go for k by 8, that would be even faster design, because all that k by 8s are going to do their tasks simultaneously. So k by 8 means 4 ripples. So 4 ripples plus what you need is just one more multiplexer level. So 4 plus 1 plus 1 plus 1, so 7. So 7 steps and your result is there. So in 4 steps, all of the k by 8 bit adders are going to complete their task, and just you need to select which uh, which is the right answer, right? So I have left that as an exercise, so you can do that yourself. For that, you need to have a proper understanding of that. So if k by 4 bit adders are replaced by k by 8 bit adders, so what benefits in terms of cost? Obviously, there is no benefit in terms of cost, because you are going to incur more cost in this case. You're adding more adders, even though k by 8 is half of that, but there are going to be more adders added to it, more multiplexers added to it. Speed obviously is an advantage, because you are going to do it much quickly, right? You need to design the whole diagram. So what you need is you are going to have a multiplexer at this point as well, and then it's going to be somewhat similar to this thing here, right? So you can try to do it yourself and see whether you have understood how this design works. But the main thing here is that we are not depending on linearly on k. The effect of k has been reduced, so you can go for higher number of k's for this design. Each level over here multiplexer is going to work at so if you have got k by 8, you need 3 levels of multiplexers, right? So this is how the overall time is going to be short. Any questions here? Try to do it yourself and you're going to see that it's not very complicated. Any questions here?
No, sir.
Okay, so if we go on and try on reducing till we reach a single bit, right? So if we started with k by 16, then we got for k by 4. In my exercise, I gave you k by 8, but you can keep on decreasing the ripple effects till you go to a single bit, and this means that all of these bits are going to be pre-computed with both 0 and 1s, right? So that would be the fastest design, because then you just have to select the multiplexer. That design is called as a conditional sum adder, right? So it's an extreme of the carry select adder. So if you go for 1 bit block, then you are going to have in other words, if I was talking about this thing here, so in a 1 bit block, what you're going to do is, if I have this 1 1 0 0 1 0 1011 and 1001, so 1011 and 1001. Okay.
Sir, if we take this one as an example, then k by 4 would be a one block adder.
Uh, k by 4, no, okay, k by 4 in that case, yeah, that would be the 1 bit adder, right? But conditional sum adder is a little different than that, because in conditional sum adder, what you do is you don't really design it as a ripple carry adder. Okay, so I'll come to that, right? So what we are trying to say is this uh, leaving the first one, all the others are going to have both 0 and 1 at their inputs to the full adder. So they you need how many? Who gave me that answer, Fahad?
Yes, sir.
Okay, you gave that answer. That was correct over here. So the only problem is that we are not going to design it as a ripple carrier. I'll come to that. So you can go with the same design k by 4. In that design, what you were doing was you were having here, yeah. So the first one is not getting any two inputs, but the remaining are getting 0 and 1, 0 and 1, 0 1. So the same thing is happening over here. That what we are doing is we need two full adders for every one of these. So 1 1 1 1 is going over here with a 1, and then in the second full adder what we have is, I'm not, okay, it's a little difficult to draw over here in this case. Okay, so we have a 1 over here, and then the second one is also getting 1 1, but with a 0 over here. So I've just tried to draw this thing out. Um, this one here only. So this is going to be one of them. So you need two full adders for every one of them, and then one over here and 0 over here. So you're going to see that all of them are going to get their outputs in just one step, because every number is known. So you don't have any ripple over here, right? You don't have any ripple over here, because no one is giving an input to another level. So you just have three numbers, so all of these three numbers are known. So when you have the case like this, that is called as conditional sum adder, right? Now the only difference in that case is that instead of designing it as a ripple carry adder, what we do is we have a different circuit for that. So this is the circuit. So instead of a ripple carry adder, what we have done is uh, we have the inputs over here. We have an OR gate and an AND gate, an XOR gate, and an inverter. So it's a simple circuit. So both the bits are going to come over here, and you're ORing them as well, you're ANDing them, and you're XORing them as well, and you're getting these four results, right? So if that's the sum, you know that two bits if XORed are going to be the sum for carry in at 0. But if carry in is 1, then you're going to get the invert of that, because it's 1, so it's going to be invert of that. And the carry out would be taken as an AND in this case, and if the carry input is 1, it's going to take it as 1 in this case. So a full adder is a little complicated circuit over here, but we have uh, actually full adder is a simple circuit over here. We have designed, but you would have needed two of those XOR gates. So instead of two of those XOR gates, what we have done is having using one XOR gate and 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 OR, we have designed a much simpler circuit than that. So that's the only difference over here. Otherwise, you could take the same k by 4 bit adder analogy to see the same thing happening on 4 bits. But the only difference here is we are not having a ripple carry adder, but we are having this hardware circuit with every bit, right? So that what I have shown over here is a full adder, but it's not a full adder. It's not going to be a full adder. It's going to be that circuit. So instead of this whole thing, what we can do is have it replaced by a simple OR gate. And okay, so it's going to be very difficult to draw an OR gate over here. Okay, I'll try. No. Okay. No. Yeah, so you got the point, right? So an OR gate, an AND gate, and an exclusive OR gate in this case would be giving us the results. So yeah. So instead of having two full adders, what we can do is have this thing over here, and then it's going to do the same thing, right? So this is my point here, that if you do this, then the cost of the whole design would be approximately k times log 2 of k plus 2 plus k of c1, where c1 is the cost of this circuit here, right? In the book there is derivation for that. It's an approximation. Obviously it gets a little complicated, so they have approximated it. So the time you can see here is time of this circuit plus log 2 of k. So if k is 32, log 2 of k would be 5. So that those are the the 5 multiplexer levels. So in this conditional 7 adder, there are going to be more multiplexers because you have shrunk the size of the ripple if carry adder to a single bit, so that there are no more ripples. So what you have to do then is to just select those answers, and for that you need more multiplexers. So log 2 of k means that if k is 32, then log 2 of k would be 5. So 5 levels for multiplexers and 1 level for T1, and all of these 32 circuits like these will work independently and at the same time. So all of them, they are going to be 32 of those circuits, and all of them are going to get their 2 inputs, and they are going to give 4 results, and all of them are going to do that in this time unit T1, right? Then what you have to do is just select their results, and for that you need obviously something similar to the previous case, that you cannot select that immediately. You have to select them first in this case, first over here, and at the same level over here, then at the next level, then at the next level, then at the next level. So it's always going to be half, 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 right? So you are going to divide that into halves, and each two will get their results. Each two will get their results if there are more. So each two are going to get their result, then there would be another result, then there would be another. So likewise, there would be 5 multiplexer levels to select from if you are talking about 32 bits, right? So this is another adder, conditional sum adder. So it's even faster than the carry select adder because you're talking about doing it without any ripples. Okay, so this design is also good, and you can implement a fast adder using this. But when you're talking about fast adders, normally there are parallel adders, and there are different techniques that we are not going to consider. If you are going to go for a course of parallel processing, then we discuss about those adders there, how to do parallel additions, but not over here. So we are just discussing about simple adders in this case, right? So are there any questions on conditional sum adder? It's just the idea of carry select adder to its extreme.
Yes, sir, it's clear.
Okay. Then we have the last of adders here, and this is actually not an adder, but it's kind of an adder. It's not a complete adder, in other words. We call it as carry save adder. Now, what happens is this is your ripple carry chain. Now, if you cut that chain, and instead of uh, propagating it to the next level, if you cut all of these chains, and instead of these carry outs going to the carry inputs of the next full adder, you save them, then it's called as a carry save adder. Now what do you mean by saving them? We are going to use them at another level, right? So it's going to work in levels. Now this type of carry save adder is more suitable for multiplication operations. So in multiplication operations, what happen is that we have many partial products to add together, and the number of inputs, the number of your results, or you can say uh, the partial products. The number of partial products keep on increasing as the number of bits increase. So you have got many numbers to add together, and for that case, a carry save adder is a better choice. So that's the only difference here. So we have broken that ripple effect, and we are going to save them and use them at another level. Another level means that the result of this would be used with uh, the next full adder at this point. So I'm going to come to that. Okay. At the end, what you need is a carry propagate adder to finally get your results, right? So carry save adder is sometimes also called as a 3-2 counter or 3-2 reduction circuit. So what happens is at each level, what you are doing is they are having 3 inputs, right? So the 3 inputs are going to give you 2 outputs. Now, one of that output is at that level. The other one is actually for the next level. So we show it like this. We show it like this. Now, for 3 inputs, we are going to show that it's going to give one result over here, at that level, the second one is at another level. So we are not trying to add anything over here. We are just trying to reduce them from 3 to 2. Okay, we are trying to just reduce them from 3 to 2, and similarly we are going to do that for the next levels, and in the end what we are going to get are just two numbers, and then we can use any of those adders that we have discussed to get a final answer. I'll come to the exercises here. um, so we can have a half adder and a full adder as well. So if you have got a half adder, we have got three, these dots are basically bits. So we have got three dots here to add, and three dots are going to give our two outputs. So one is at that level, another is at the next level. If you have got two dots, that's a half adder. You can use a half adder to do that addition. Again, there would be one result over here, another level, and then you have a slight mark over here to show that this is actually a half adder, right? So this is a little terminology that we are going to use. Okay, so let's go for a simple exercise again in dot notation first. Now let's say we have to add seven numbers together. Now these are the seven numbers. So one, two, three, four, five, six, seven. Now these are the seven numbers that you have to add together. How you're going to, each dot here is a bit. Each dot here is a bit. So how you're going to do that, right? So if you go for a carry propagate adder or a carry select adder or any of the adders that we have done, they work on just two numbers. So what you can do is add these two together, these two together, these two together, get their results. So then you're going to get multiple results. Then you're going to add, or you can, what you can do is add the first two, then add it with the next one, then add it with the next one, and then add it with the next one, and then add it with the next one. So you're going to take a lot of steps to do that, right? And each time your addition gets a little complicated, and it gets a bigger as well. So you need a very big um, ripple carry propagate adder or a carry ripple carry adder to do that addition. Now in carry save adder, we are not adding them, we are reducing them from 3 to 2. Now when we reduce them from 3 to 2, for each block shown over here, is this visible? Because I'm going to, okay, let's try to have it a little bigger.
The dotted blocks are visible.
Okay, so I'm going to have a little bigger so that it gets a little more visible. Now what's happening here is these are the seven numbers. So what we are going to do is we are going to take three bits from any level, and these three bits are going to go to a full adder. So all their these dotted rectangles that you are seeing are actually full adders, right? So there are 12 full adders that we have used, and each full adder is then going to give you one result that is going to go to that level, and another result that is going to go to the next level. Okay, so for the first one, we can see here that the first one we have here is going to give us a single bit over here, and this is its carry out. For the second one, it has got a single some bit over here and its carry out, right? Uh, wait. Yeah, and the third one over here, it's just copied over here. Okay, so these 7 bits have reduced to just 3 bits. Okay, let's go for the next level. In the next level, do the same thing over here. So 3 bits getting one bit at this level and 1 bit another level. These 3 bit getting 1 bit at another at this level, and this copied together over here. And you're getting 2 bits from the previous level. So in total, you have got 5. So what you have done is reduce those 7 numbers into 5 bits over here. Okay, that you have to add finally, right? So what's happening in this level, we have used 12 full adders to reduce these 7 numbers into 5 numbers. And if you use 6 more full adders, what you're going to see is you're going to reduce it from 5 numbers to 4 numbers. And then if you use six more full adders, then you're going to reduce it to just three numbers. And finally, if you use some more full adders plus and half adders shown over here as well, then you can reduce it to a number which is just having two. Uh, uh, they are just two numbers over here. Now, finally, you can use a 7-bit adder to get your final result. So in carry save adder, let me just do it over here. So in carry save adder, what's happening is that you have not added these numbers. What you have done is you have just, so let's say we have these three numbers. Okay, the three is easy. Okay, so if we had to add these four numbers together, now as I've mentioned that carry save adders are mostly used for multipliers. So okay, so we get many partial results, partial products. So we just have to add all those partial products, get a final answer. So it's more used over there. So we have, so it's not in the same straight line, but let's just assume that this is a straight line. So 1001. So what we can do is these three can be given to one full adder. These three bits can be given to a one full adder. These three bits can be given to one full adder, and these three bits can be given to one full adder. So we have used four full adders, right? So a full adder, as we have seen in the last class, has got three inputs, one, two, and carry input, right? And it's going to give one and two outputs, a sum and a carry out, right? So what we are doing is we are giving a one over here and a zero over here and a zero over here. So, or you can give a one over here or zero over here, zero over here. The thing is that you have these three inputs, and you have three inputs in a full adder. You can give any input to any side, so that's not a problem. So this full adder is going to give you a result. So it doesn't matter if there is a one over here or here or here, as long as there is a single one, right? So it's going to give two outputs, a sum and a carry out. Now one output, the sum, which would be in this case one, is going to go on this level, and the carry out, which would be zero in this case, is going to go on this level. This zero is simply copied over here. Again, 111 is going to give a 1 over here and a 1 over here. And this 1 is simply copied over here. Okay. And 10110, are you getting it? Because if you have any problem, just ask me. If anyone has any problem in understanding what's happening over here, just ask me. We are
Yes,
going to
sir.
use we are going to use four full adders, and in a full adder we have got three inputs, and here we have selected three inputs. So you have to just see that a full adder gets three inputs, and it's going to give one result over at this level, another one at another level. And so the same thing happens over here, that 010 is going to give you 0 as 1 as a sum, and 0 as a carry out, and then you have 1 copied at this level, and again 101 is going to give you a 0 at this level and a 1 at the next level and 0 copied over here. So you have seen that we have reduced it from 4 inputs to 3. We have not done any addition like a ripple effect over here. So there are multiple four full adders, and they are independent, right? So they are not depending on each other. They are independent four full adders that we have used in our design in this case, and we have obtained a result in just one operation, right? So this is our first operation. So we are going to get this. Then in the next one, we are just simply going to do the same thing over here. So if there are 2 bits, you are going to leave those 2 bits, because the final answer needs just 2 bits. So we are going to leave this. We are not going to use any half adder over here. But here we are going to use a full adder. Here we are going to use a full adder. Here we are going to use a full adder. And what you're going to see is, if you have got 3 more full adders, you are going to get an answer Okay, so I don't want to go to the next page. I'll try to do it over here. So okay, I'll try to do it over here. So 10 is simply copied. You're not using anything over here. 101 is going to give a 0 over here at this level and 1 over here at the next level. And then since there is no input coming from this side, so this input is blank over here. 111 is going to give a 1 over here and a 1 to the next level. 000 is going to go 0 over here and a 0 to the next level, and then there was a 1 over here. So now you can just simply add these numbers. I have introduced a 0 over here because there is nothing coming from this. So now you can use a 5-bit ripple carry adder or any other adder to get your result. So you can see carry save adder is not a proper adder. It's just a reduction kind of thing. So it tries to reduce it using full adders. So every full adder is a 3 to 2 reducer. So if you're going to give 3 inputs to it, it's going to reduce it. It's going to reduce it into two bits. You're going to use 1 bit at this level, another level, and you're going to repeat it. Just so using just 7 full adders, what we have done is obtained this result. And the end we need a 5-bit carry, uh, ripple carry adder or carry propagate adder, whatever you can have. So carry propagate adder and ripple carry adder are the same thing. You can have carry save adder, conditional sum adder as well. You can have carry select adder, any adder you want. So that's the last stage here. So I'll come back to my address page over here. Okay, so in this design, when we have got 7, so it has reduced from 7 to 5 to 4 to 3 to 2. So what in total what we have used is 28 full adders, 1 half adder, and a 7-bit adder at the last step. You could have used this is just one option, but you can have it in a different way as well. So if, for example, had used a half adder in this case over here, so you would have added one more half adder to this. But what will happen is if you have used a half adder, then there would be a single bit at this point and just 2 bits at this point. So instead of a 7-bit adder, you would have needed just 6-bit adders because 2 of your bits are finalized, right? So a better design could have been if you have used a half adder at this point. So as I mentioned, this is just one way to do it. The number of steps are not going to change, right? So number of steps are still going to remain the same. Only your last carry propagate adder is going to be a little smaller, right? So instead of 7-bit, it would be 6 bits, but still the number of steps are going to remain same. So you could have used one full adder at this point to reduce this size of this 7-bit adder to 6-bit adder, right? Then it would be a 6-bit adder, 28 full adder, and 2 half adders. Okay, so this is about carry save adders. This is how the reductions have happened at each point from 7 inputs to at each level. It's showing you how many bits are there to be added, and then finally what you get is something like this, and carry propagate at the end is going to give you your final answer, which would be um, the result of that addition. Okay, right. So are there any questions here? Yes, anyone? I know there should be some questions.
So this one is clear.
It's okay. Okay. So we are going to use these carry save adders in multipliers. And I'm going to come to that once more. Um, so this was about the short introduction of additions, and we have introduced some new adders. Uh, this was just to give you an idea how additions are performed. Basically, when you're talking about all of these, we are saying that we have to go stick with two's complement number system because that's the number system that is used mostly. It's easy to do addition subtraction over there, uh, and also since it's a little difficult to do multiplication in that case, but still we can do multiplication over here. Okay, so our next topic would be multiplication, but we are going to take a small break, right? So we are going to take something like 15 minutes break over here. uh, we are going to come till 7:45. Okay, so I'm going to close this meeting and I'm going to again open it again, right? So that would be easy. So you can disconnect and then you can rejoin. Okay, so wait till I just take your attendance over here. Okay, so your attendance is here. Okay, so we are going to come after say 15 minutes, 10:45. Okay, inshallah.